Okay, so there's a lot of different results in mathematics. There's results which have important philosophical implications, and there's results which are mostly just used for doing calculations. I remember hearing someone say a long time ago that most mathematicians don't have time to care about philosophy very much because there's just so many calculations to be done and so many times when the important thing, the sort of task in hand, is just how are you going to calculate a particular thing. And, the time to step back and wonder what it really means in the grand scheme of things is sometimes lacking. Now, the Yoneda lemma is one of the most useful results in category theory for calculations, but it also has very broad philosophical implications. It's the kind of result which, for me at least, I found it really changed my perception on, what spaces are, what shapes are, basically what things are. Okay, because it really goes into the sort of core matter of category theory, which is, or one of the core matters, which is how can we refer to particular things. You see, there's at least two ways you can describe a mathematical object. You can describe it kind of internally. So let's say you have a graph, for example, a load of dots and arrows. You can describe it as just that. You can say, well, we have a set of dots and we have a set of arrows and they touch each other in certain ways, and that describes the graph. That's a kind of internal description of it. That's a description of the graph kind of from inside. But one of the main kind of ideas in category theory is that we also want to have these kind of external pictures of things. So we want to be able to describe mathematical objects, not just kind of internally, but sort of externally. We want to be able to describe them with respect to their relations to other things. And if you think about the real world, this is also true to some extent in the real world. For example, if you wanted to describe a particular person, you could describe them from a kind of internal perspective. What's the layout of their physiology, how is their brain wired up, and so forth. Or you could describe them from a kind of external point of view. Where do they live, who are they friends with, etc. And so we have these kind of two different ways that we think about things, and the Yoneda lemma connects them together. So one of the main ideas in category theory then is that you can describe an object in a category by referring to the sort of arrows around that object and what other objects it's related to in different ways. And we've seen this happen in the category of sets, and I've kind of hinted in these videos that it's possible to do that in more general categories. But with the Yoneda lemma, we're really going to see exactly how this works, and it's just such a amazing result. I mean, it's such a short kind of result, but there's like so much there. I mean, you can just it really, to me, it really gave me a big sense of wonder to see how all these mathematical objects have this kind of dual nature. They have the kind of internal definition and the external definition, and it even makes one think about things like particle physics and the structure of the universe and the kind of fractal nature of a lot of reality. It's really a very interesting result. Now, to begin with, let's just remember about this category set. Okay, so this has sets as objects and the arrows are functions. Okay, so one of the things I did in my first video in this series was say something about how we can talk about sets and we can sort of pick out the particular details of things from this kind of categorical view, where we don't look inside these objects and say, oh, well, this object represents a set with 3 elements, for example. No, what we do is we just think of these as objects, and we think of the functions as arrows, and simply by looking at that conglomeration of dots / objects and arrows between them, we're able to actually identify what things are. So how did this work? Well, one of the key things for us in the category of sets was to identify this singleton set, a set with just one element. And if you recall, that's a terminal object in the category of sets. It has the property that for any set, there's just one arrow into this singleton set, this terminal object. And that arrow corresponds to a kind of function which collapses all the elements in our set down to our singleton set. So we see that this set here has a property that for any other set, like this one, there's just one arrow, one function into it. So okay, we can determine the set that has one element just by looking at the arrows and the objects. But we can do much more than that, because once we have this singleton set, once we know which object represents it, we can then find out about other sets. So for example, we can ask, how many arrows are there from this object here to this object here in the category of sets? And we find that there are 2. There's one arrow which kind of injects this singleton element into this first element of our set, and then there'll be another arrow which sends it to the other one. So we can essentially refer to the elements in a general set as arrows from the terminal object into them. Okay, so that's nice. That means this category of set does indeed have this sort of property that I was talking about, that we can refer to the objects and if you think about it, we can also describe things like what the actual functions are and so forth, just by looking at the relations, by taking this kind of external or relational kind of view of what the objects and arrows are. Okay, so that's nice, but what about other categories? So another very nice category is this category of graphs. Okay, so this category of graphs, it has these directed graphs as objects, and then the arrows are so-called graph homomorphisms. So an arrow in this category of graphs is a pair of functions. One function that sends the vertex set of our source graph to the vertex set of our target graph, and another one, indicated by these dotted arrows, which sends the edge set of our source graph to the edge set of our target graph. So for example, this homomorphism here sends these 2 vertices to these 2, and it sends this directed edge to this directed edge. And the only property we require these graph homomorphisms to have is that the source and target of the image of an edge are the images of the source and target of that edge. So basically the graph homomorphism works in a way that it kind of, so basically the graph homomorphism has to work in a way that it kind of preserves the incidence of the kind of structurally preserving transformation that you'd probably naturally think of. Okay, so those are our arrows in this category of graphs. I'll go into this in more kind of technical detail later. But what I want to indicate here is that in this category of graphs, we actually have a similar kind of results to what we see in the category of sets. This kind of idea that if we have a graph, let's say this one here, yes, of course it has an internal description. We can describe it as these vertices and these edges with some incidence relations. But more than that, we can also refer to this graph in an external kind of way. So just like in the category of sets, we can sort of talk about these elements of our sets as if they're basically just arrows from this terminal object. So we can think of this terminal object as a kind of template, which is like injecting its information into the particular elements and sort of referring to them. And in the category of graphs, well, we have this graph here, which just has a single vertex. And we can basically think of the vertices of a general graph as corresponding to arrows from this singleton graph here, this single vertex. And so we could refer to this vertex here as an arrow from this to this. We could refer to this vertex here as an arrow from this to this, and so forth. And so there's a way to describe the vertex set of a particular graph, just in terms of arrows from this graph which just has one vertex. So okay, that's great, but there's obviously, okay, so that's great, but it begs a couple of questions. The first one is, how do we actually identify this graph here, which just has one vertex and no edges? How can we kind of refer to that in a categorical way? And secondly, probably more importantly, it begs the question of how do we describe the edges of a particular graph? Well, the way that we can describe the edges is kind of similar. We can have this other kind of fundamental type of graph, which just has two vertices and a single arrow, kind of single edge. And again, we can think about graph homomorphisms or arrows from this kind of graph into our graph of interest, and we can use those to actually refer to the particular directed edges in our graph. Okay, so this is really quite remarkable. I mean, we could identify this graph here as something which has, so we can sort of say that this graph here has the property that there are three arrows into it from this single vertex graph here, one picking out each of its vertices, and there are two arrows into it from this graph here. Now, is that enough information to actually tell us which graph here we're talking about? Well, if you think about it for a bit, you probably discover that the answer is no, okay? Because that information, just saying how many arrows there are into this from these different things, yes, it tells us that we're talking about a graph which has three vertices and two directed edges. But there are other graphs which have three vertices and two directed edges. For example, there's this one here, which is different, okay? So we need more information. In particular, we need a way to really talk about not just what the constituent elements are within this kind of graph, not just what it's made out of, but how the things it's made out of are joined together. And like, this is one really beautiful aspect of a Yoneda lemma, is that it explains how we can talk about such things from an external kind of point of view. So internally, the way that we'd talk about this is we'd say, okay, we have two edges, and this edge here has this vertex as its target, and this one as its source, and this one has this as its target, and this is its source. That's enough information to describe this internally. But how would we describe it externally? And the kind of magical idea is that we have these fundamental kind of types of graphs, sort of elementary particles in the universe of graphs, if you like. And we can think about the interactions between them, the arrows between them, and somehow they actually represent, and somehow the way that the kind of interactions between them are related to the kind of injections into our structure of interest, reflects the way that the internal kind of elements of our structure are interconnected. So in particular, how could we say, from a sort of external point of view, how could we communicate that this vertex here is the source of this edge here? Well, a way that we can do it is we can say, okay, there's an arrow from this directed edge here to this edge here of our graph, and there's an arrow from this single vertex graph to this vertex of interest, but there's also an arrow kind of externally which sends this vertex here to the source of this directed edge here, and it has the property that if we go along this arrow and then we go along this arrow, we get the same thing as if we go along this arrow. Composing this with this gives our yellow arrow. And if you think about it, that information is a kind of external way of saying that this is the source vertex of this edge. Now, this is just one example, okay? And I'm talking about graphs in this example. But the Yoneda lemma very, very neatly describes how to do this in general. It's actually, once you get your head around the terminology, it's much easier to get your head around. So once you get your head around the terminology, it's much easier to sort of understand what I'm talking about here with this kind of internal versus external ways of describing things, just using the Yoneda lemma. It's a very, very useful calculational, it's a very, very kind of computational tool, and it's very succinct. Now, my main goal in this video is to explain what the Yoneda lemma is, what it says, and so forth. And hopefully by the end of it, you'll have this kind of appreciation of these kind of different ways of referring to things. And believe me, it's much more general than just talking about graphs. There's so many different types of categories which the Yoneda lemma can be applied to. And in so many of these cases, we see how it really gives us this kind of dual way of describing things. And I mean, to be honest, I think it's extremely beautiful, and I think we're very lucky actually in this day and age that like category theory is just taking off, because to be honest, a lot of this sort of territory is unexplored. People are starting to realize things like the profound implications of things like the Yoneda lemma and what it really means for the kind of, well, I might say what it means for the kind of philosophy of form, really, and, you know, what things really are and how we should think about, you know, what shapes are and so forth. But more than that, I think it's brilliant that we live in this kind of age when these ideas are around, things like the Yoneda lemma, which, you know, gives so much insight into the sort of true nature of things. But on the other hand, these are all very new kind of ideas, and there's not many people who know enough category theory to actually, you know, be able to run with these things. Now, of course, that's a bad thing, but the other side to it is that it's on us to sort of take these results and try and understand them. And I think there's so much new kind of ground to be covered and new kind of places that we can take these ideas and apply them and use them to gain new insights. So for the pioneering type amongst you, this is a very fruitful kind of opportunity. Okay, so the Yoneda lemma is expressed in terms of functors and natural transformations. Basically, what I'm saying is that to understand what the Yoneda lemma says, we're going to have to take a kind of high-level view of what these kind of structures are. So, for example, we're going to have to really think about what a graph is in terms of category theory. Now, in my previous video, Category Theory for Beginners, Graphs and Dynamical Systems, I go through this kind of way of thinking about these structures in detail. So it might help you to watch that video first. Although I'll try and go over the basic ideas quickly. Okay, so here's a graph. It has these vertices and these edges. So we need to think about how we can describe this thing properly. For example, how would we put this in a computer program? And one way to do it is to say that we have a set of edges, in this case A and B, so there's our set of edges, and we have a set of vertices, 1, 2 and 3, there they are, and then there are two functions which sort of describe how this structure is connected together. There's a source function which sends every edge to its source vertex. So for example, this edge here, A, starts from vertex 1, so its source is 1. So this function g of s, this thing that gives us our source vertex, sends A to 1. Okay, and similarly it sends B to 2 because edge B here starts at vertex 2. Now, the other function we need is the target function. This is going to send an edge to its target. So it sends edge A to 3 because this edge A points at 3. Okay, so this is our way of talking about what a graph is in kind of concrete terms. It's a set of edges and a set of vertices and a function which we'll call g of s, which sends every edge to a vertex, which is thought of as its source. And then there's this other function which associates an edge with its target vertex. Okay, so if you think about it, any kind of graph can be described in these terms, and it's a nice sort of language because it allows us to do things, for example, like have many arrows from one vertex to another. But there's another kind of layer to this, because we can actually think about this kind of representation as a functor. Okay, so in that previous video, I described how we can think of this category of graphs as, we can basically write it like this. So what this means is that the graphs, the objects in this category, are functors from this category here with two objects and two parallel arrows to this category of sets. Okay, so let me explain how that works again. So let's draw out this category here a bit more clearly. We can draw it like this. It has an object called E, and it has an object called V, and it has these two arrows which we call S and T. There's also identity arrows, but I won't bother drawing those. Okay, so this itself is a category. Okay, and what I'm saying a graph is it's going to be a functor from this category to the category of sets. Okay, so all of this gubbins, we think of all of this as just a few things which are going on in this category of sets. Okay, we have these sets and these functions. And so how can we think of this as a functor from this category here to the category set? Well, we can imagine there's a functor which associates this object E here with this set, and it associates this object V here with this set, and it associates this arrow here with this function g of s, and it associates this arrow here, t, with this function g of t. Okay, and this has to be a functor. Okay, so that's all I'm going to say about this. If you're still confused at this point, I encourage you to watch my video on graphs and dynamical systems, because I build up this intuition more gradually. But basically, we can think of a graph as a functor which associates the kind of edge object with an edge set, the vertex object with a vertex set, and this arrow here s gets mapped into a kind of function which picks out the source vertex of a particular edge, and similarly for this t arrow here becomes this target function. Okay, so we'll have many different graphs, and each of these different graphs corresponds to a functor from this category here to the category set somehow associating this E with a set, this V with a set, and these arrows here with these kind of functions which tell us which edges are connected with which vertices. Okay, so that's the basic way we can describe what a graph is. A graph is a functor from this category here to the category set. Okay, so we have many different. Okay, so we have all these different graphs. We kind of know now what the objects are in this category. But obviously, this being a category, it doesn't just have objects. It doesn't just have these functors which pick out particular graphs. It also has to have arrows. Okay, we have to somehow have arrows between our different graphs in this category. So how are the arrows defined? Well, the arrows in this are just natural transformations between these different functors. So let me illustrate that next. Okay, so now we know how to talk about graphs. For example, I've said how we can describe this graph here as this functor G from this category of two parallel arrows to our category set. Now, of course, the category of graphs has many graphs. So here's another one. I'm calling this graph A, and it corresponds to this functor from our parallel arrow category here to the category set in this way. Okay, so this functor here sends this object E to this set here, just a single element here representing this single arrow, and it sends V here to this vertex set of two elements, 1 bar and 2 bar, and when the and then the S and the T arrows are sent to these functions A of S and A of T, which are telling us which vertex this edge starts at and which vertex it ends at. Okay, but in the category of graphs, of course, we also have arrows between graphs, graph homomorphisms. So here's an example of graph homomorphism. It goes from our graph G to our graph A. I'm calling it A for arrow, okay? And the way that this particular graph homomorphism works is it sort of takes this graph and folds the two arrows on top of each other and sends them there. Okay, so it is a graph homomorphism. It preserves the source and target of edges, okay? But how can we talk about these graph homomorphisms like alpha here? How can we talk about these arrows in our category of graphs in terms of functors? Okay, well, the idea is that an arrow between graphs is precisely a natural transformation between functors. Okay, so here we have a functor G representing this graph here, and we have a functor A representing this graph here, and a natural transformation from G to A is precisely this kind of graph homomorphism here, this kind of arrow in the category of graphs. Okay, so how do we set up this particular homomorphism? Well, what's it going to be? It's going to be a natural transformation from G to A. So how do natural transformations work? Well, a natural transformation has a component for each object in our kind of source category here that we're making functors from. And so there's going to be two components to this natural transformation. We can call them alpha E and alpha V. Now, alpha E is going to be an arrow in the target category, which goes from where E got sent under the first functor to where E got sent under the second functor. In other words, alpha E is just going to be a function from the edge set of our first graph to the edge set of our second graph. And it's basically what I've drawn with these dotted arrows here. So we can think of this as a sort of graphical representation of the eth component of this natural transformation alpha. Or we can just draw it more concretely like this. So that's going to be alpha E. It goes from where E got sent to under G to where E got sent to under A. And because it's landing in the category set, it's actually a function, okay? Arrows in set are functions. Next thing is we need a similar kind of component for V, okay? So this is what I've drawn with these solid arrows here. So these solid arrows are representing alpha of V. This is the kind of V component of our natural transformation. It makes sense in the context of graphs. If you're going to transform graphs, you have to say, where are you sending your edges to? That's alpha E. And where are you sending your vertices to? That's alpha V. In our kind of functor picture here, this is just going to be an arrow which goes from where V got sent to under G to where V got sent to under A. So in this case, with this picture, it sends 1 and 3 to 1 bar. And it sends 2 to 2 bar. So that's going to be alpha V. Maybe I'll make these arrows dotted here to correspond with the picture below. Okay, so this is our picture then of what a arrow is between graphs. It's a natural transformation from this functor G to this functor A. Now, such a natural transformation has to have these components, but it has to also satisfy an extra condition called the naturality condition. We have to have these kind of commuting squares for every arrow of our source category. Okay, so we have two arrows in our source category, S and T, and these get sent to different functions over here in the category of sets. And so there's these kind of squares that we can walk around in this picture, and we require that paths around these squares give similar results. More specifically, for this edge S, we can see that S gets sent to A of S under this functor A and G of S under this functor G. And so we require that there be a kind of naturality square associated with this arrow S. So what that means is that if we do this if we go along this arrow alpha E, the eth component of our natural transformation, and then we compose that with this arrow A of S, we have to get the same results as if we go along this square the other way around. So if we go along G of S and then alpha of V. So let's write that condition down. So we require that A of S after alpha E equals alpha V after G of S. So what this condition is saying is that if we look at where this S arrow got sent to under these different functors, it has to make a kind of commuting square with these components of the natural transformation. Okay, and it boils down to this condition here, that A of S after alpha E equals alpha V after G of S. And in order to have a natural transformation, all we require is that there's a kind of commuting condition like this for every arrow of our source category. So we have one other arrow, which is T, and so we're going to have a similar condition for the T's. So that's just going to say that A of T after alpha E is alpha V after G of T. What do these two conditions mean? Well, what they're really saying is basically what a graph homomorphism is. Something that preserves the kind of source and target vertices of the edges that it maps. In particular, what's this equation mean? Well, what it's basically saying is that the source of the image of an edge is going to equal the image of the source of the edge. Okay, and similarly, this is just saying that the target of the image of an edge is going to equal the image of the target of the edge. Okay, so these are really natural conditions for a kind of transformation of graphs, probably part of why we have the name natural transformation for such things. Okay, so that's the whole story then. We know that the graphs are functors from this category here to set, and we know that the arrows are natural transformations. And if this seems particularly alien to you, I recommend you watch my video on graphs and dynamical systems, where I explain this more gradually. So it's really rewarding to get one's head around these levels of abstraction, because it allows us an amazing amount of compression with regard to the kind of structural things which we're representing. In particular, we can just write a very, very succinct little expression here to describe what's going on in our pictures. To basically say that we have this category here with two dots and two parallel arrows. This is just a kind of small picture of this category here. That's our sort of template category that we're making graphs out of by doing functors from it. And we're saying we have these two graphs, G and A, which correspond to functors from this category here to the category set. And then we have this natural transformation alpha from this functor G to this functor A. Okay, so now we can start to see why this here is notation which means the category of graphs. This basic notation means this is the category of functors from this category here to the category set. Okay, in fact, if you want to connect even more neurons together, you might notice that this is an exponential object in the category of categories. However, we're not going to need that kind of information today. The important thing is to understand that the graphs correspond to functors and the arrows between the graphs correspond to natural transformations. And of course, also, you should notice that we could have many other different kinds of categories instead of this one, which we could consider functors from. So these are kind of set valued functor categories, and there's an amazing amount of different mathematical structures which you can describe. Another example being the category of dynamical systems, which we'll get onto later. And basically these kind of functor categories are extremely natural ways of representing families of mathematical objects, and these kind of functor categories have some extremely nice properties. In particular, for us today, the Yoneda Lemma applies to them, which gives us this wonderful insight. Another thing which is true of these kind of categories is that each of them is something called a topos, and we'll get on to topos theory later, but basically it means that there are sort of special parts of these kind of categories which represent logic and the way that spaces interrelate, and it's just absolutely magical stuff. But today we're going to be talking about how the Yoneda Lemma applies to these kind of functor categories. Okay, so we've recapped this language of functors and natural transformations, and we've seen that these kind of functors that go into the category set can often be interpreted as kind of structured sets, okay, as in the graphs we've just talked about. Now, in addition to natural transformations and functors, there's one more thing that we need to know about, another piece of terminology, before we can discuss the Yoneda Lemma. And this is the idea of Hom sets. So it's really quite a simple idea, maybe a little bit strange at first glance, but here goes. The basic idea is, suppose we have some category and we have some objects. So let's say we have an object N and an object X. Now, there may be some arrows in this category going from N to X. In particular, there will be a set of arrows going from N to X. It may be an empty set, but there will be a set. And so this set of arrows from N to X, this is what's known as the Hom set. Okay, so it's written Hom N, X. And this is simply the set of arrows which goes from object N to object X. Now, I must admit, I do find this terminology a little bit annoying. Why is it called a Hom set? Well, I think it's a kind of abbreviation for the set of homomorphisms from N to X. Remember that some category theorists like to call arrows morphisms and sometimes call arrows homomorphisms. Okay, so this is kind of an abbreviation for the set of homomorphisms from N to X. Maybe a better kind of terminology for it would be to call it the arrow set from N to X. Some people would call this C N, X. So it's the set of arrows in C which go from object N to object X, where C is this category that we're working in. Okay, maybe this notation is a little bit better, but I'm sticking with this Hom notation because that's kind of standard, and there we go. Another way we might refer to this kind of collection of arrows in certain categories is we might call it x to the power of n. Okay, so this would be an exponential object. Don't worry too much about that if this seems peculiar to you, because we're not going to use that terminology, but it just happens that in some categories we have these exponential objects, which are sort of objects which somehow represent collections of arrows between other objects, but we won't worry about that today. So simply, Hom N, X, for Hom sets, N, X is the set of arrows from N to X. So what? Well, we use this to define something called a Hom Functor. Okay, so this Hom Functor is denoted Hom N, blank. Okay, so there'll be one of these Hom Functors for every object N in our category C. And as you can see, this is a functor which goes from our category C to the category set. So what does it mean? Well, basically, this is a functor which somehow sends objects in the category C to the category set. And this n here is really part of the sort of name or definition of the functor. So how does it work? Well, it's pretty simple, really. Here's an object x in our category C. And the way this functor works is when we operate this functor on this object x, it gets sent to a set, of course, because this is a functor sending objects to sets. Because this is a functor sending objects of category C to sets. So which set does this functor send this object x to? Well, it sends it to the set of arrows from n to x. Okay, so simply this Hom functor here, Hom n comma blank, when we operate it on an object x, we get the Hom set n comma x, the set of arrows from n to x. So in this case, there's two arrows from n to x, which we call it a and b, and so this Hom functor is going to send x to this set a and b. Okay, so this is kind of half of the story, because this is a functor, so we need to say how it works on objects, what we just did. The other thing we have to say is how it works on arrows. And this is a bit more detailed, but it's quite intuitive, okay, if you think about it. So suppose we have some general arrow in our category C. Let's say we have an arrow F from an object X to an object Y. I've drawn it here. Well, when we lift this arrow under our Hom functor, it gets sent to an arrow which we write like this, Hom n comma f. And this ought to be an arrow which goes from Hom n comma x to Hom n comma y. Okay, so remember, Hom n comma x and Hom n comma y are just sets. Okay, so here's the set Hom n comma x. It's the set of a and b, these arrows out of n into x. And here's Hom n comma y. It's these three arrows C, D and E, which go from n to y. So how can we make a function which sends arrows coming into x from n to arrows coming into y from n using this arrow f? Well, if you think about it, there's a very natural way to do this, and that is that if we take an arrow, let's say an arrow A here, which goes from n to x, that's going to be a member of Hom n comma x. And then if we just compose this arrow f after A, then that'll give us an arrow which goes from n to y. In this case, as I've written here, we'll suppose that C is actually equal to f after A. And so what this means is that when we operate this Hom n comma f function on this arrow little a here, we get this arrow little c. Okay, so what I'm saying basically is the way that this function's defined, which sends arrows from n to x to arrows from n to y, is when we operate this function here, Hom n comma f, on an arrow little x from n to capital X, what we do is we just compose f after little x, and that'll give us an arrow which will go from n to y. So you can see I've written how Hom n comma f works in this case. Okay, so this is basically how this Hom functor works. Okay, it maps objects to the set of, it sends an object to a set of arrows from n into that object, and it sends an arrow into this kind of function which translates one Hom set to another by composing with the kind of arrow which we're lifting under this Hom Functor. Okay, so if this is the first time you've seen this, I suggest you kind of pause the video, draw out a category or two, and kind of play around with this and try and get a feeling for how this Hom Functor works. Perhaps you'd also like to convince yourself that this is actually a functor when we're working with a general category C. Okay, and of course there's going to be one of these Hom Functors for every object M. I should also say, just for completion, that there's actually another kind of Hom Functor as well. We're not going to talk about that yet, but there's another kind of Hom Functor which works kind of the other way round, which we denote as Hom dash and then some object X. And that's a kind of different type of Hom Functor. It has a similar definition, but we'll talk about that properly later. For the moment, it's definitely going to suffice just to use this kind of more straightforward Hom Functor here, Hom n comma blank. And this is the kind of final thing we need to know, and now we can talk about the Yoneda lemma and this fascinating result. Okay then, so here comes the Yoneda lemma. Here it is. So what's it say? Well, it says that if we have any category C, and suppose we have a functor G from the category C to set. Okay, so a good example of this would be when C is this category here, in which case a functor from C to set could be thought of as a graph. Okay, we've discussed this, but the Yoneda lemma is more general. Okay, it just says if we have any functor G from a category C to set, then this statement holds true. What's this statement say? Well, firstly, nat. What does nat mean? Well, simply, nat of f comma g for functors f and g, this just represents the set of natural transformations from functor f to functor g. This is when, of course, f and g are going to be two functors, in our case going from this category C to set. Okay, and this is just the set of different natural transformations between them. That's what nat f comma g means. Okay, so the Yoneda lemma says that the set of natural transformations from this functor to this functor is isomorphic to this functor G operating on this object E. Okay, so this is a very, very general statement. It holds for any category C and any object E of this category C and any functor G from C to set. And this is what the Yoneda lemma says. Now, if this is the first time you've seen this, you're probably quite confused by this, right? Because there's a lot of different machinery of category theory all mixed together in this kind of equation here. Okay, we've got isomorphisms, we have a set of natural transformations, we have this Hom Functor, some other functor, lots of things going on. But once we unpack this, you will hopefully see that this is such a kind of sensible result, and it's the kind of thing that you really can get a lot of intuition from. So the best way to understand what this means is to look at an example, okay? And then we're going to go back and look at this Yoneda lemma in more detail. There's actually a little bit more to the Yoneda lemma than just this. It's actually a stronger condition than just an isomorphism. This is actually something called a natural isomorphism. We'll talk about that later. Let's just start by looking at an example, okay? I should also say that the real magic of the Yoneda lemma is actually in the proof, okay? Because it's how we construct this isomorphism, which is really important. But the proof is actually amazingly straightforward. It's like a 3-line proof or something. So anyway, once we have a look at an example, this is going to make a lot more sense. So let's pick a category C, okay? How about this one? This is our kind of category of 2 parallel arrows, which is the thing we're using to make graphs, okay? As I was saying at the beginning of the video, graphs can be thought of as functors from this category to the category set, okay? So we'll talk about graphs. Now we need to pick an object E of this category C. We'll actually pick this object E up here, okay? So it's going to look like I'm talking about graphs now, but of course remember that this is a general statement. It just happens that I'm using an E here and an E here, just so I can step straight into an example, okay? So they're all the things we need. Now, what does this Yoneda lemma say? Well, okay, so we have a category C, there it is. We have an object E of category C. The other thing we need is a functor G from C to set, okay? So what's a functor from this category to the category of sets look like? Well, it's a graph. Here's an example, this graph here, okay? We talked about this one already. It has 3 vertices, 1, 2 and 3, and these 2 edges, A and B, okay? So how do we represent this graph as a functor? Well, it's here, okay? So we have, we think of this graph as a functor from this category C to the category of sets. It sends this object E to this set G of E, which has 2 elements, these edges A and B, okay? And it sends this object V here to this set of vertices 1, 2 and 3, okay? So this functor here is representing this graph essentially. It sends this S arrow here to this function, which picks out the source vertices of our edges, and similarly T gets sent to G of T, picking out the target vertices of our edges, okay? So this functor just represents this graph. Now the real magic of this is to understand what this means, okay? What is Hom E comma dash? Well, that is a Hom Functor. That's what I just discussed on the last load of writing on the blackboard. And what it really is it's just a functor which goes from this category C to the category of sets, okay? And so remarkably, in this context, that should be a graph. Well, that's interesting, isn't it? Because this is obviously a fairly special kind of functor, because it has this kind of natural definition in terms of this actual sets of arrows of the kind of template thing which we're using to make graphs. Okay, so it ought to be a fairly important graph. So let's find out what graph this is. Let's calculate what this Hom Functor is. Okay, so all we need to do is think about how this Hom Functor Hom E comma dash operates on the different objects and arrows of our category C. So let's start by determining what Hom E comma E is. So that's where this object here, E, is going to get sent to under this Hom Functor. Okay, So what's Hom E comma E? It's just the set of arrows from E to itself. Okay, so there's just going to be one such arrow, and it's just going to be the identity arrow of this object E. Okay, so this is just a set with one element, which we call IDE. Okay, so far so good. Now there's just one other object that we have to operate our Hom Functor on, and that's V. Okay, so the next question is, what's Hom E comma V? That's going to be where this object gets sent to under this functor. So what's that going to be? Well, that's going to be the set of arrows from E to V. So let's draw Hom E comma V down here. So what are the arrows from E to V? Well, there's two of them, S and T. So this is a set S, T. Okay, so we're nearly done. We've operated our Hom Functor on the different objects of our category C. All we have to do now is operate our Hom Functor on the different arrows in this category C and see what kind of functions they get sent to under this Hom Functor. Okay, so let's just remember the definition of our Hom Functor. So the way it works, just in general, okay, just for a second forgetting about this specific category that we're talking about, the way this works is that if we have an object E, maybe we have a load of arrows from that to some object X, okay, maybe here's a specific arrow, little x, and then suppose we have an arrow F from X to Y. Well, then what's going to happen to this arrow little x? Well, it's going to get sent under this lifted Hom Functor, Hom E comma F of X is going to equal F after X, okay? So this lifted Hom Functor sends this arrow X here to F after X, okay? So this is the effect of doing Hom E comma F on this element here of this Hom set, okay? That's the definition we've already looked at. Okay, so now let's use this kind of intuition here, and we're going to use it in this specific case of our category C. Okay, so let's just pick an arrow and figure out what happens to it when we lift it under our Hom Functor. So how about this arrow here, S from E to V? Well, what's going to happen when we lift it? We're going to get Hom E comma S, and that's going to be an arrow which goes from Hom E comma E to Hom E comma V, right? And so it's somehow going to send arrows which go from E to itself to arrows which go from E to V. How is it going to work? Well, we can just use this formula here. Okay, so in this case, this formula becomes Hom of E comma S operating on an arrow X equals S after X. So okay, that basically tells us then how this arrow is going to get lifted under this Hom Functor. So what's it going to do? It's going to be a function from this set here to this set here. And how does it operate on an element x of this set here? Well, it sends it to s after x. So in particular, there's just one element in this set here, which is IDE. And when we do s after IDE, we just get s. And so this here is going to be the function Hom E, S. Now, in a pretty much analogous way, we can figure out what happens to this arrow here, t, when we lift it under our Hom Functor. And that's just going to be another function from this set here, Hom E, to this set Hom E, V. This time it's going to send this identity thing to t. That's going to be the effect of this other lifted arrow here, Hom E, T. Okay, you may want to pause the video and check out for yourself that this works. Now ask yourself, what kind of graph would this represent? Okay, it's a good question. We're going to get to that in more detail in a moment. Let's just make sure we've finished this job of figuring out how we lift all these different arrows. So if we're going to finish this job, we then, if we're being very methodical about this, we'd then want to ask, okay, what happens to this arrow here, this identity arrow of E, when we lift it under this Hom Functor? In other words, we're now curious about what is Hom E, IDE. And if you think about it, this is going to be an arrow which goes from Hom E, to Hom E, And how does this arrow work? Well, in fact, it has to just send everything in Hom E, to itself. Okay, indeed, we need this kind of condition that when we operate our functor on an identity arrow, we get a resulting identity arrow. Okay, that's one of the things we require of a Hom. That's one of the things we require for something to be a functor, and indeed, this Hom thing here is a functor. So all this Hom E, IDE is it's simply an identity arrow of the edge set here. And in a similar way, this arrow IDV just gets lifted to an identity arrow of Hom E, V. Okay, so we don't need to draw those in. This is the important part of the picture here. This is a sort of representation of what our Hom Functor looks like without drawing in the identity arrows. Okay, and you can see that it has a kind of similar layout to this. And why is that? That's because this represents a graph. Which graph does this represent? Well, this is the kind of magical bit. So which graph does this Hom Functor represent? Well, this would be the edge set and this would be the vertex set. So we have one edge, which we'll call IDE, and we'll have two vertices, S, which is the source of this edge, and T, which is the target of the edge. So this is a graph, and we can rightly call this graph Hom E comma dash, or Hom E comma blank, okay? This Hom Functor here represents this graph. Now this is a very elementary graph, this is a very important graph. As I said before, this kind of graph has the property that we can really identify things about any other kind of graph by thinking about the arrows from this graph to it in the category of graphs. Okay, so now comes the moment of realization, because what's the Yoneda Lemma saying? It's talking about natural transformations from this Hom Functor here to G. What's a natural transformation? In this case, it's a arrow in the category of graphs from this graph to this graph. Okay, so here's an example. We might send T to 3, and we might send S to 1, and we might send this edge here to A. Okay, so that would be a natural transformation from this graph here to this graph here. It would be a natural transformation from this Hom Functor here to this other functor here, G, which represents this graph. Now, what's the Yoneda Lemma saying? It's saying that the set of natural transformations from this graph here to this graph here, or equivalently from this functor here to this functor here, is isomorphic to the thing we get by operating our functor G on E. So what's G of E? Well, it's just the edge set of our graph, okay? So this is what I was saying at the beginning. The edge set of our graph, each edge in our graph corresponds to a kind of arrow from this special sort of single edge graph to G. Okay, so something quite profound is happening. The Hom Functor here, which is this kind of very natural functor in the Yoneda Lemma, turns out to be, in this example of graphs, it turns out to be this special kind of elementary graph. And what the Yoneda Lemma is saying is that the set of natural transformations from this Hom Functor to another functor, in graph language, the set of graph homomorphisms from this single edge graph into our other graph, is isomorphic to G of E. What's G of E in this context? It's just the set of edges of our graph. So the Yoneda Lemma is telling us that the set of edges in our graph, each edge in our graph corresponds to a natural transformation, an arrow in the category of graphs from this special kind of template graph into our graph G. Okay, this is basically explaining to us how the structure of G, how its bits and pieces, well, its edges in this case, are being put in correspondence with these kind of special arrows coming out of this special kind of template graph. Indeed, this special kind of template graph, this single arrow is really picked out because it corresponds to this special kind of Hom Functor, this special functor from C to set, okay? And there's more to the Yoneda Lemma. So, I mean, in this case, we picked this object E. In this case, it was this object here. What do you think would have happened if instead we'd picked this object V? Well, in that case, we wouldn't have got this graph here as our Hom Functor. We would have got, can you guess? We'd have got this graph here, a single vertex. And indeed, the vertices of our graph correspond to arrows from this single vertex. And there's even more to it, because the Yoneda Lemma also has an extra kind of layer to it, which I haven't mentioned yet much. And what this extra layer is, this is the finished result, is not just saying that this set of natural transformations is isomorphic to G of E. The Yoneda Lemma says that this set of natural transformations is naturally isomorphic to G of E. It's natural in both G and E. Now, I haven't explained what that means yet, and I will get round to it, but the long shot of that is basically that by looking at the interactions between these different Hom Functors, we can actually talk about which edges are connected to which vertices. And, you know, the amazing thing about all of this is that graphs, this amazing category of graphs, is just one example in an infinite number of examples that this Yoneda lemma can be applied to. And in every case, it's explaining exactly how this kind of internal, external sort of relationship works. Okay, so perhaps I'm getting ahead of myself a little bit. I'm extolling the virtues of this result, but I haven't really explained it properly. And I think the best way is for me to sort of sketch a proof of the Yoneda lemma. Now, this might sound intimidating with all this kind of exotic gadgetry going on, but in fact, the proof is remarkably simple. It's so simple, it's just very, very short. Actually, this is really just a proof sketch. What I really want to do is to describe what this isomorphism is, because basically I'm saying that there's a sort of correspondence between the natural transformations from this Hom Functor to this functor and the elements of this set, the set that we get by operating this functor G on this object E. Okay, so I'm going to go through this argument now. I'm using these kind of symbols which all seem familiar from this example of graphs, but you should bear in mind that this is a completely general type of argument. Okay, so what we really want to do is to make a natural transformation from this Hom Functor here to G. Okay, so what do we know about such a natural transformation? Well, we know that for every component, say the VF component of these functors, there's going to be a VF component of this natural transformation which sends, say, Hom E comma V to G of V. Okay, here V is just any object in this category C. Okay, so we know that our natural transformation is going to have a component alpha V. And because all this stuff's just happening in set, this is just going to be a function from this set of arrows from E to V to the set of elements of G of V. So all we're going to do is think about what these kind of natural transformations will look like. Okay, so the one thing we do know about them is that for every arrow, say an arrow from E to V, we're going to have a naturality square like this. Okay, and so we have this naturality square, so we know that going along alpha E and then G of S gives us the same function as going along Hom E comma S and then alpha of V. Okay, so we know these two functions have to be the same, and this has to hold for every arrow coming out of our object E. Okay, so we want to construct such a natural transformation. So let's just ask ourselves, do we know of any elements which are going to be in this set here, Hom E comma E, in a general category? Okay, so what's Hom E comma E? It's the set of arrows from object E to itself. Okay, so what kind of elements are definitely going to be in that kind of set? Well, there's just one that we can be sure of being there, and that's ID E. Okay, now I've written this in red and it represents an element of this set. Okay, now what happens when we apply alpha of E onto this element here? Well, it's sort of like what's going on over here. Okay, we're going to do some kind of natural transformation. It's going to have an ETH component, and that's going to send this element somewhere in G of E, isn't it? So alpha E is going to look like that. Now, in a general context, of course, there may be more elements in this set. There may be more arrows from Hom E to itself. So we know that IDE is going to get sent to some element of G of E. So why don't we give this element a name, okay? We'll call alpha E of IDE, we'll give it a name, we'll call it E star, okay? So there it is. It's just going to be some element of this set here, G of E. So in this kind of context, IDE gets sent over here. So we could call this E star, okay? Over here, it's like that. Now, let's just continue to think around this naturality square. Okay, so the next thing we're going to do, going this way around the square, is we're going to do G of S on E star. So what are we going to get down here? We're going to get G of S of E star. Now, all we're going to do now is we're going to go the other way around this naturality square. Okay, so we take IDE and then we want to apply this function here, Hom E comma S. Now, remember, in general, the way this works is that Hom E comma S operating on X gives us S after X. Okay, we've already talked about how this works. So for us, our X is just IDE. So what happens when we operate this function on it? Well, we simply get S. Now, all we do is we apply alpha V onto S. And what do we get? We get that this must be equal to alpha V of S. And that's the end of our argument. So what does this mean? Well, it really means something quite profound, okay? Because what's happened here, let's say we want to know what this natural transformation alpha is doing. Okay, we made one choice in this construction. We made one choice, which was to send IDE to some particular element of G of E. We called that element E star, okay? And everything else about this natural transformation has actually been fixed by that choice. Because if we want to know what the V component of our natural transformation is for a general object V, well, we do know that. Why? Because we know what happens when we do alpha V on an element S. What is this element S? It's just a general element, a general arrow from E to V. And we know that alpha V operating on S is equal to this, G of S of E star. And this is going to hold for every arrow S from E to V. In other words, it's going to hold for every element S in Hom E comma V. In other words, this equation here, if we think of S as varying in this set, this is telling us how alpha V works on every single member of this set. So it's actually telling us exactly how this function alpha V is defined. And this holds for any object V. So if we have any object V in our category, don't be confused by this connection with the graphs, because this is all general kind of arguments here. This can hold in any category C, and E can be any object, and S can be any arrow from E to any other object V. And in general, we always have this kind of equation holding true. So this describes the isomorphism between the set of natural transformations and the elements of G of E. Why? Well, because given any element, E star, of G of E, we can always define a natural transformation like this. So we can always define it so that it sends the identity element of E to this element E star, which we've picked out of G of E. And that then forces the rest of the natural transformation into having a particular form. Conversely, if we have a natural transformation, alpha, we can just see how that operates on IDE, and that'll pick out the kind of labeling element of G of E. So this is really describing an isomorphism between these. So now we kind of know what this isomorphism looks like, we can be a bit more descriptive here. So I'm going to actually write what these functions are here, what this isomorphism actually is. So I'll write it as psi subscript E comma G, and it has an inverse which we can call psi to the minus 1 E comma G. So how is psi defined? Well, psi of E comma G operating on an element E star of G of E is going to give us a natural transformation alpha. Where alpha V of S equals G of S of E star for all arrows S from E to V. Okay, and what about the inverse? Well, the inverse is pretty simple. So alpha E comma G inverse operating on alpha is just going to be alpha E of IDE. Okay, so how does this work in the context of our graphs then? Well, what it's saying is, for example, let's say we're talking about a natural transformation from Hom E comma dash to G. Well, what we're saying is that if we're going to send IDE here, this kind of labeling of our fundamental edge, if we're going to send that to some edge E star of our graph, well then we know how this natural transformation works on the rest of its components as well. In particular, we know that for this element S here of Hom E comma V, in other words, we know that for this kind of source vertex, we know that the Vth component of this natural transformation, alpha of V, is going to send S to what we get if we operate G of S on E star. What do we get if we operate G of S on E star? We get 1. Okay, so going around the naturality square this way is sort of like doing our natural transformation, you know, sending our edge to where it's supposed to go, and then looking internally where its source is, and then going around the naturality square this way is sort of looking at the Hom Functor and looking at where this sort of source vertex is, and then doing the vertex component of the natural transformation on that, and they're giving us the same thing. Okay, so it's really saying in this context that just by specifying how this fundamental edge is getting mapped, the rest of this natural transformation has been fixed. Okay, so this is the basic layout then. It's time for a little bit of clarification about the general and the specific, because in this kind of argument I'm sort of mixing discussion of the general Yoneda lemma with this particular example involving the graphs. Okay, so just to clarify, what I'm writing here, this is a general statement of the Yoneda lemma, and this works for any functors going from any category C. And down here, this is the sort of general argument for the Yoneda lemma. I won't exactly say it's a proof because I haven't shown that this kind of isomorphism which I'm constructing here is a natural isomorphism. I'll talk about that a bit more later. But I have given the sort of basic idea of how we construct it, how we can take an element E star from G of E and use it to define a natural transformation. And this is the sort of basic way that we relate elements of this set G of E with natural transformations from this Hom Functor to G. Okay, and then up here I've written the general kind of description of this isomorphism. So we'll actually have one of these isomorphisms, psi of E comma G, for every object E, of which we sort of construct a Hom Functor about, and every other functor G from C to set. Okay, and then the other stuff on this board is about this specific case of graphs. Okay, and so what I'm trying to do with this example is to sort of show an application of the Yoneda lemma. So I'm basically saying in this case we're going to use the isomorphism going this way round. So we're basically imagining that we are thinking about doing a graph homomorphism, or if you like, a natural transformation from this Hom Functor to this functor representing our graph. And the way we're doing this, let's say, is we have this Hom Functor, which basically corresponds to just a graph with one edge, and we're saying, okay, imagine that we're just specifying how the eth component of this Hom Functor is mapping this element here, this IDE, which is really representing the single edge of our graph. And we're saying, well, if we're fixing it so that IDE is getting sent to E star under this alpha E component of this natural transformation, then that fixes the rest of the natural transformation. How does it fix it? Well, it's described here. Okay, we're saying that given this element E star of G of E, the rest of the natural transformation is fixed, because for any object V and any arrow S from E to V, we're going to have this equation holding true. So the V component of the natural transformation operating on this S is going to be G of S operating on E star. Again, this is general notation up here. So I do have a specific S involved in this talk of graphs, this arrow S here, but this is just a sort of coincidence in a sense, because over here when I'm talking about S, I'm talking about a general arrow S from E to a general object V. Okay, but in this specific case of graphs, yes, I do have a particular arrow which I have named S, And we can see how the way that alpha v, which in this graph case corresponds to the kind of way this graph homomorphism works on vertices, we can see that the way that that's working on this source vertex here is described by this. So in particular, what's this statement say? Well, what's alpha v of s? Well, alpha v is going to be the sort of v component of this natural transformation, and we can see, you know, by how our graph looks like, we can see by this picture here how this is supposed to be drawn. And the Yoneda lemma says that alpha v of s is sort of fixed by the way that we've mapped IDE. It's fixed by this equation to be g of s of E star, which is the source of E star. So we know that alpha v of s is 1. Okay, so there it is. Now we also have another arrow from E to V. We have another arrow like this, which we're actually calling T. And, you know, we could just use this same equation and put T's in here instead. And then, of course, we get that alpha V of T is going to equal a G of T of E star. So, in other words, this sort of V component of this natural transformation has to send T here to number 3. So this is a drawing then of the V component of our natural transformation as it's working on these kind of edge sets and as it's working on this vertex set here. So there we are. Okay, so now let's talk about the specifics again. Let's talk about this specific example of graphs. Okay, so the thing is, we've already seen some evidence that this Hom Functor here turned out to be very special for describing graphs, because it turned out to just be a single edge. Okay, and it turns out in general, when you're dealing with these functor categories, which are sort of categories of structured sets, and there are many of them, they're very important, and if you're interested in one of them, then it turns out that these Hom Functors are very important, because the arrows out of them, the natural transformations out of them, basically tell you about the structure of other objects in your category. This is what the Yoneda lemma is about from this perspective. Okay, and so it's a good idea to get all the Hom Functors. That it's kind of like a collection of elementary particles that describe the rest of the goings on in your category. Okay, so we have one of them, and how did we get it? Well, it's Hom E comma dash. So we got it by picking this object E. We picked this object that represents the edge set. So let's get the other one. Let's get the other Hom Functor and see what that looks like. So we just pick the other object of our category C here, which is V, and now we're interested in what's the form of Hom V comma dash. Okay, this is another Hom Functor, and in this case it can be visualized as another graph. Okay, so we'll just, well, I've sort of shown how to construct it here. Okay, so all we do, we say, okay, well, we want Hom V comma E. What's that? Well, that's the set of arrows from V to E. Well, there aren't any. Okay, so that's just going to be the empty set. Now, the other object of this is going to be Hom V comma V, which is the set of arrows in category C from V to V. Well, there's just one such arrow. That's the identity arrow of this object V. So Hom V comma V is just a set with a single element. Okay. Now, we think of this as the edge set, and this is the vertex set when we're thinking of this functor as a graph. So we have a graph with no edges and one vertex. And so we can draw it. Okay. And here it is. And you probably anticipated this. This is the other sort of fundamental elementary kind of graph. Just the graph that has one vertex and nothing else. And we can now rightly call this graph Hom v comma blank, because that's the functor that it corresponds to. Now, I've just gone through a bit more work here to flesh out what the rest of this Hom Functor looks like, because I think it's quite useful. It's actually a really great exercise to make these Hom Functors and to sort of go through them, because it really validates a lot of the kind of language which we use and even the kind of observations which we've already seen, for example regarding empty sets and things like that. So I've already described the two objects. So I've already described how this Hom Functor works on these two objects. Okay, it will send E to this empty set and it will send V to this set with one element. Of course, this Hom Functor also works on the arrows. So how does it do that? Well, a funny case, maybe the funniest case to contemplate, is what happens to this arrow S from E to V when we lift it under this Hom Functor, Hom v comma blank. Well, this arrow S from E to V is going to get lifted to become an arrow from Hom v comma E to Hom v comma V. So it's going to be a function from this empty set to this singleton set. And how is this function defined? Well, if you remember the way that this these sort of arrows lifted onto under this Hom Functor defined, they send an element x to the arrow S after x. Okay, so it's going to be a function from this set to this set, and it will take an element from here and send it to S after that element, a composition. Okay. However, this set doesn't have any elements, so this is a bit kind of vacuous. We've sort of defined a function, we've defined how it works on inputs, but it doesn't have any inputs. So this is a function from the empty set to IDV. So we actually have encountered this idea already when we talked about initial objects. I think it was in so I think it was in my video on functors and duality, or round about there I talked about this. So there is this curious idea in the category of sets that if we have an empty set and we have another set, then there is a function from the empty set to the other set. It sort of doesn't have any inputs. So in fact, it's just one weird kind of function that doesn't do anything, even though we seem to have actually programmed the function to do a specific thing. It doesn't have anything to do that thing on. So there you are. So okay, that's Hom v comma S. It's a funny case. What about this arrow, just to make sure we've seen the different cases? So this is an arrow in this category C, this IDV. It goes from object V to object V. So when we lift it, we're going to get this arrow here from Hom v comma V to Hom v comma V. And how does this arrow, this function, work? Well, it takes an element and then it sends it to IDV after that element. Okay, this is like arrow composition. Here, this this sort of arrow with a line before it, this is notation mathematicians sometimes use to mean maps to. Okay, so this is a function which maps x to IDV after x. In other words, this is the image of x under our function. Okay, so how does this work? Well, there's just one element for it to work on, which is IDV, and it just takes it and composes it with IDV, which gives IDV. Okay, so this is just an identity function. So we can rightly say Hom v comma IDV is ID Hom of v comma V. It's just the identity function on this set. Similarly, there'll be an identity function on this set, which is the image of IDE, and there should be similar stuff drawn over here, which would be the images of these two arrows, which would give identity functions of these two sets. I didn't bother drawing those. I didn't want to have too many things coming out new at the same time. So as you can see, a lot of this is pretty vacuous. The only really important thing here is that this corresponds to a graph with one vertex, so we can draw it over here. So it's basically just a graph with one vertex and no edges. Okay, so now we get to an issue that's really interesting to think about, which is, okay, so now we have this. Let me ask you an interesting question, which is, if you're working in the category of graphs at this kind of high categorical level, where you're just sort of looking at the objects and the arrows, how can you say that this vertex here is the source of this edge? Okay, now we can refer to this edge using this natural transformation from this single arrow graph here, as I've already talked about. We can also refer to this vertex here in terms of a natural transformation from this single vertex graph, this thing we can call Hom v comma blank. So we could say that there's a natural transformation beta, which looks like this, okay? This will be the v component of beta. The eth component of beta is sort of vacuous, okay? It doesn't really have any elements to work on. There are no edges to map, okay? So we could draw this on our diagram as well, in terms of the sets. It's going to start looking a bit messy maybe, but let's try. So that's going to be the v component of beta, and then the eth component of beta is just this kind of function without inputs, like so. Okay, so this is a drawing then of this natural transformation from this functor Hom v comma e to this functor g that represents our graph. And here I've actually drawn it graphically. Okay, so thinking about the graphs again, we have a arrow alpha which picks out this edge A, which I'm saying is E star, okay, and we have this arrow beta which picks out this vertex 1, okay. So how can we say that these two arrows are talking about the same vertex? Well, this is really quite magical, I think. What we do is we say, well, imagine there's a natural transformation gamma, which goes like this, okay? So that'll be the v component of gamma. So gamma is some kind of natural transformation which sends this vertex to the kind of source vertex of our single edge. And moreover, this is the important bit, let's suppose that beta is equal to alpha after gamma. Okay, and this is our key kind of way of externally describing that this vertex is the source vertex of this edge. By saying that if we sort of send this vertex into our by saying that if we send this vertex to be the source of our single edge graph, and then we send our single edge graph into this graph here, and that doing so has the same effect as sending this vertex over here, that information is communicating that this vertex gets sent under this transformation beta to the place which is the source vertex of where this edge gets sent to. Okay, so this is an external way of describing how these bits and pieces in this graph are connected. And we could describe the rest of the information in this graph in a similar way. We can say, well, there's a arrow from here to number 3, which is the same thing we'd get if we compose the arrow from here into T and then alpha. And that would pick out this vertex 3 and say that's the target of this edge. And we could have other arrows representing this edge B, and more of these kind of triangles of natural transformations to describe how vertex 2 is the source of B and vertex 3 is the target of V. So there's a collection of arrows from these Hom Functors and kind of arrows between them with these kind of equations representing commuting triangles, which describe the whole structure of this graph, but they describe it from a kind of external perspective. Okay, and we actually get a better description of how all this stuff works from the Yoni Lemma. Okay, because there's this other kind of level to the Yoni Lemma which I haven't discussed yet, which is basically saying that this isn't just an isomorphism between these two sets, it's a natural isomorphism, and it's in that kind of naturality that we see how this kind of stuff works. I should just draw this natural transformation gamma in this set language as well. Okay, so it's a natural transformation from Hom V comma dash to Hom E comma dash. So actually I want to give this natural transformation a more kind of elaborate name. I want to actually call it gamma superscript S, just to remind me that it goes from this single vertex to the source of our arrow graph. Okay, so I should actually say beta equals alpha after gamma superscript S. So this S here, this isn't like a component or anything, this is just a name that I'm just putting upstairs. Okay, so let's draw gamma in the set language as well. So there's the VEF component of gamma S, and again the kind of EF component of gamma S is a bit sort of vacuous because it doesn't have any inputs. Okay, so I've just cleaned up this picture a little bit. I thought I'd only write the Hom V comma V since Hom V comma E is empty, and I've deleted a lot of these kind of vacuous arrows which were here. So this is basically just what was here before. I've just kind of cleaned it up a bit and deleted some of the empty sets and arrows which are sort of vacuous. Okay, and what I've written here is something in general. Okay, so we're keeping shifting between the case of talking about the graphs, because that's really illustrating the Yoni Lemma, and also then talking about the kind of generality. So now I want to talk about the generality of it. And what I really want to talk about is how we can make a natural transformation from one Hom Functor to another Hom Functor. Okay, so this gamma here was an example of that in the graphs, but I want to talk about this in general. Okay, so in a general category C, let's suppose we want to cook up a natural transformation from Hom V comma dash to Hom E comma dash, where V and E are just general objects in our category C. Well, we can do it if we have an arrow S from E to V, and then we can make a natural transformation which we can call gamma superscript s. How do we make it? So what we want to do is that for every object x of our category C, we want to have an xth component of this natural transformation, so gamma s of x, and that ought to go from where x got sent to under our first Hom Functor to where x got sent to under our second Hom Functor. So gamma s of x ought to be a function which goes from Hom v comma x to Hom e comma x. Okay, so what we want to do is we want to make a function which sends arrows from v to x to arrows from e to x. And this is in our category C, okay, our general category. So let's suppose we have an arrow u from v to x. How are we going to map it under this function here? Well, a way we can change it to get an arrow from e to x is we can do u after s. So that's how we define this function here, this x component of our natural transformation. We define it so that if we have an arrow u from v to x, then we send that arrow to u after s, okay, and that will give us an arrow from e to x. And we're going to use this very shortly when we talk about this isomorphism here being natural in objects E of our category C. Okay, so I believe at this point a quick aside to recap what natural isomorphisms are would be a good idea. Okay, so let's just consider a general situation where we have categories D and E and functors L and M, each going from D to E. So I think I've talked about natural isomorphisms before in this series, and there's several equivalent ways to define them. And I think the definition I went for before was to say that it's a natural transformation psi from L to M is a natural isomorphism when there's another natural transformation, psi to the minus 1, from M to L, such that composing psi and then psi to the minus 1 gives the identity natural transformation on L, and similarly composing psi to the minus 1 and then psi gives the identity natural transformation on M. Okay, so that's just a fancy way of saying that a natural isomorphism is just an isomorphism between objects L and M in the category of functors from D to E. If this seems unfamiliar to you, don't worry, we're not going to build on this because I'm actually going to tell you an equivalent definition of a natural isomorphism. So basically, we'd say that psi, being a functor from L to M, is a natural isomorphism if it's a natural transformation from L to M and each of its components is an isomorphism. Okay, this is an equivalent way to define a natural isomorphism. Okay, so we just require that each of these arrows, each of these components like psi of x from L of x to M of x is an isomorphism between these two objects. And that will be an isomorphism in this case, in this category E here. So there's something else which is relevant to our discussion, and that is that if we want to prove that psi is a natural isomorphism, we just have to show that psi is a natural transformation and that psi of x is a natural isomorphism, and then it will follow that psi to the minus 1, this natural transformation obtained by gathering together all the inverses of these components, is also a natural isomorphism. It's the sort of inverse of this one. Okay, so we can see this quite easily. because we'll have to have naturality squares like this in order for psi to be a natural transformation. Okay, and then supposing that psi is also and supposing that each component psi of x is a isomorphism, that means it has this kind of inverse psi to the minus 1 of x and so forth. And we can show that psi to the minus 1 is also a natural transformation. So how do we do it? Well, the fact that this square is natural implies we have this equation here. And then all we have to do is multiply it by psi, the y component of psi to the minus 1 on the left, and the xth component of psi to the minus 1 on the right. Now, this doesn't change the equality because we've done the same thing to both sides of this equation, but what does happen is that these two cancel and these two cancel because each of them become identities, and what we end up with is this new equation that psi to the minus 1 of y of after m of f equals L of f after psi of x to the minus 1. And what does that mean? It means that this square is natural, okay? L of f after psi of x minus 1 is psi of y minus 1 after m of f, okay? So this square is natural, so we've now shown that psi to the minus 1, made out of these kind of components, is also going to be a natural transformation. So what I'm basically trying to say is that if you have a collection of arrows, one arrow for each object, in this kind of natural transformation style, if you know each of those arrows is a isomorphism and you have the inverses, then if you can just show that that collection of arrows forms a natural transformation, then you know that you have a natural isomorphism, and you know that the collection of inverses of those arrows is also going to be a natural isomorphism, the inverse of what you have. So how this becomes relevant for us is because we have, in the case of the sort of Yoneda isomorphism, we have these psi's and these psi to the minus 1s, and I choose to show that the psi to the minus 1s are sort of natural, and that's the way I argue for the naturality. But you see that you can work with the psi to the minus 1s, or you can work with the psi's. Either way, showing that collection is natural implies that the collection associated with the inverse is natural as well. Okay, so let's carry on talking in generalities, and I'm now going to move on to this thing which I kept hinting at, which is that there's a bit more to the Yoneda lemma. It's not just that this isomorphism here puts the elements of G of E and these natural transformations in one-to-one correspondence with each other. It does that, but it's more than just an isomorphism. It's a natural isomorphism. So what does that mean? Well, basically, if you have two functors, then you may have a natural transformation from one to the other. And what is that natural transformation? Well, it's a load of components. For every object of your sort of source category, there's one of these components of the natural transformation, an arrow, okay? And sometimes arrows can be isomorphisms. And if every component of the natural transformation is an isomorphism, then we call such a natural transformation a natural isomorphism. So what I'm saying then is that this psi thing which I've defined, relating G of E and this set of natural transformations, is a natural isomorphism. So what does that mean? Well, one thing it implies is that it's a natural transformation, okay? But how can it be a natural transformation? Natural transformations go between functors, right? So somehow that means that this G of E, when we consider, somehow that means that this G of E can be considered to be a sort of value of a functor, as can this, okay? So how do we think of these things as functors? Well, I'm trying not to load too many new ideas into one video, but it's difficult with the Yoni Lemma because so many things are going on at once. But basically we can consider this to be the value of a functor on an object, and this to be a value of a functor on an object. So what do these kind of functors look like? Well, they're functors which go from C times set to the power of C to set. Okay, so if this seems a little abstract, don't worry. We're kind of going to skirt around this. We're not really going to have to get into depth about what this means. But basically what I'm saying is that we can consider there to be a functor which goes from the product of these two categories to the category set. Okay, what does that mean? Well, what it basically means is that it's a functor that takes an object of C and it takes an object of this category and it gives us a set. Now, what's an object of this category? Well, it's just a functor from C to set. Okay, this is the category of functors from C to set. And so what this is basically saying is that this is a functor which, when it's operating on objects, it takes an object E and it takes a functor G and it gives us a set. Well, that's what this does. And surprisingly, that's also what this does. So it's quite remarkable that this G of E can actually be considered to be a sort of thing that an object in this category gets sent to under a particular functor. There's a particular functor that sort of has the outputs objects of this form. So what I'm saying here is that this psi can be considered to be a natural transformation from this kind of functor to this kind of functor. Okay, so I've already tried to demonstrate that the components of this natural transformation, this psi E comma G, are isomorphisms. Okay, and so that means I just have to demonstrate that that this psi is kind of natural in objects E of C and these functors G, these objects of set to the power of C. Okay, but that's why I'm labeling the components of psi with these two different things here, because actually this is a natural transformation between functors which are dependent on objects E and functors G. There's one extra kind of thing to bear in mind here, because what I want to do at the top is I want to argue that this psi here is natural in objects E, okay, because I don't really want to have to deal with all the sort of complicated machinery involved in thinking about these kind of functors from the product of two categories to another category. So what I'm first going to do is show that psi is natural when we consider stuff in C and we hold our functor G constant, and then I'm going to look at the other way around. So I'm going to then hold the object constant and vary the functor and show again that the thing is natural. So the other kind of extra funny thing going on here is that I'm actually, with this square, I'm about to demonstrate that the inverse of psi is natural. Okay, so it's something which is true of natural isomorphisms, that if you know that each component is an isomorphism, of course that means that these components have inverses, and you know the collection of all those inverses gives you the kind of inverse of the natural transformation. So sort of conversely, if I can prove to you that psi to the -1, the inverse of psi, is natural, then I'll have proved that psi itself is natural. So let me try and give a sort of rough sketch about why we can consider psi to the -1 as a natural transformation. So as I say, this kind of transformation kind of works in two components. It works in sort of two directions. One is where we might vary the object that we're interested in, say either an E or a V. And then the other way we might vary things is we might change the functor G. But I just want to talk about the first case to start with. So let's suppose that we hold this functor G fixed. Okay, so what we then have is that for every object E, we have one of these kind of functions, psi to the -1 E comma G. And that's going to be a function which goes from a which sends a natural transformation to an element of G of E. Okay. And so I want to show that this whole collection of sort of functions indexed by objects of C constitutes a natural transformation. So what I really want to do is to sort of fill out these naturality squares and to try and show you how this works. So we're going to do something similar to what we did before with this square down here, because these functors here, they have sets as their values. Okay, so so these arrows here are just functions. So we can just consider what happens when we put an element alpha in here, a general element, a general natural transformation from this Hom Functor to G, and we'll see what happens to it when we go both ways around this naturality square. So let's start by going this way around. So what happens when we go along this arrow? Well, we do psi to the -1 E comma G on our natural transformation alpha, and that gives us this. Okay, so what we end up with up here is psi of E of 1 of E, and sometimes we are calling that E star. Okay, so what's the next thing we need to do to go down here? Well, we just need to apply G of S to E star. So a bit like what was going on down here, we're just considering S to be a sort of general arrow from E to V, and this is all happening in a general category. Okay, so what happens when we apply G of S to this? Well, we simply get G of S of E star. Okay, now the funny bit, which is how do we go down this arrow here? So I've told you that this can be considered to be what some functor sends an object E in a functor G to, but I haven't told you how this functor operates on arrows. You see, we'll have an arrow S from E to V, and we essentially want to kind of lift that arrow under this functor that makes these things that I haven't really described properly, and we're going to see that that gives us a certain kind of function which somehow sends natural transformations from Hom E to G to natural transformations from Hom V comma dash to G. Okay, so how does that work? Well, it turns out it's not as complicated as it sounds, okay? Because we've already seen down here how we can make a natural transformation, which I'm calling gamma to the power of s, which goes from Hom of v comma blank to Hom of e comma blank, okay? We've figured out that if we have an arrow s from e to v, then we can make this thing, and it's defined so that its x component is this type of function here. And so we really have this kind of picture, okay? We have alpha, which is a natural transformation from Hom e comma blank to g, and we know how to make these kind of gamma s's, which is a natural transformation from Hom v comma blank to Hom e comma blank. So is there a way that we can combine these to give us a natural transformation from Hom v comma blank to g? Well, sure there is. We can just do alpha after gamma of s. And that turns out to be just how this function works here. It takes in an alpha and it gives us alpha after gamma to the power of s. Okay, where gamma is this natural transformation defined like so. And so all we have to do now to complete this naturality square is just to apply this psi to the -1 of v comma g to this. And that'll have to equal this. So we get that g of s operating on e star gives us psi to the -1 v comma g of alpha after gamma to the power of s. Well, we can go further because we know how psi to the -1 works. We have it here. So when we go along this arrow, then we just get psi to the -1 of v comma g of alpha after gamma s. And since we know how psi to the -1 works, we can expand this out and we can just see that that's going to be alpha after gamma to the power of s and the v component of that, and that's going to be a function operating on id of v. And since this is just vertical composition of natural transformations, we can just take the components here and we can write this as alpha v after gamma to the power of s of v operating on idv. So crucially, what we have is that this equals this. Okay, that's what it means for our sort of Yoneda isomorphism to be natural in objects of C. Okay, it means that this here equals this here. And what does this mean? Well, it means just what I was talking about down here. Okay, so let's interpret what this stuff means now in this category of graphs. Okay, we'll go back to this specific case. So what's going on here? Well, we're starting off with a natural isomorphism alpha from Hom E to G. And then when we apply this, we just see that that's associated with this edge E star, where IDE gets sent to under this natural transformation. Okay. And then when we apply G of S, we get this source vertex of E star here. So that's one way we can refer to this vertex. Now, what this is telling us is that there's another way to refer to it, and this is the sort of external way of referring to it, because it's saying that if instead we take our alpha, like so, and then we consider alpha after gamma to the power of s. Well, what's that? That's a natural transformation from Hom v comma dash, so it goes from this single vertex to G, and the way that it works is that it goes along gamma and then it goes along alpha. So it's just this beta here that I defined like this, okay? And then what this is saying is that if we then take that natural transformation and we just get this element here of it, alpha v after gamma s of v idv. So in other words, if we find out how this sends its sort of basic element, idv, into Hom e comma dash, and then we just apply the v component of alpha upon it, we'll get the same vertex, okay? So what this is basically telling us is that there's two ways we can refer to this vertex. We can say, well, you can refer to it by doing a natural transformation alpha and seeing where the main edge of that gets sent and looking where the source of that is, or you can do this natural transformation gamma starting from this single vertex and transform that vertex to the source vertex of your edge, and then just do the v component of this natural transformation, and you'll talk about the same vertex, okay? So more basically, this is telling us that when we're sending vertices into our graph in such a way that we can break that sending into these two steps, firstly sending it somewhere in the initial edge and then sending the edge in, that's a kind of another way that we can say that a vertex is a source of a particular edge. And in a similar way, of course, we could show that the vertex, in a similar way, we could externally describe when a vertex is the target of a particular edge. And if you think about it, I encourage you to do so, we can really describe all of the goings on in a particular graph just by saying, well, we have certain natural transformations from this edge graph here and this vertex graph, and then we have these natural transformations sending a vertex to a source or a vertex to a target, and we have certain sorts of commuting triangles. And that's really a totally external way of describing what's inside a particular graph structure. I mean, it's sort of reminiscent of what they do. It's sort of reminiscent of what they did in particle physics and things, where they sort of bombard a certain thing with particles and see how they bounce off each other and so on, and figure out what's inside something, okay? Okay, so I've tried to argue about what this naturality of the Yoneda isomorphism in objects means in terms of internally and externally referring to things in graphs, but I think I better actually prove that these things really are natural in these objects of category C. So we've gone around the naturality square these two different ways. So just to recap, we have alpha here, we do psi to the minus 1 of it, and we get alpha e of IDE, and then we can do g of s on it and we get this. That's one way around the square. The other way around the square, we go from alpha to alpha after gamma to the power of s, and then we do psi to the minus 1 of that. So we want to actually prove that these two things are equal. So the first thing is to look at this expression here, and then if you remember the kind of main naturality square that used to be down here, that was just sort of what we got from going one way around the square, and we know that's equal to what we would have got going the other way around the square. So we know that this is equal actually to alpha of v operating on s. We got that from our old Yoneda square. And then now we just have to look at this expression here, alpha of v after gamma to the power of s of v operating on idv, the thing that we got by going this way around. And now, if we just have a look at the definition of gamma, we see that gamma, the x component of gamma s operating on u, gives us u after s. So here's the vth component of gamma s operating on idv. So that will give us idv after s. In other words, it will give us s. So this stuff here becomes an s, and we have alpha v operating on s, just as we had up here. So that proves this naturality in objects of C. Okay, so now just to complete our sort of tour de Yoneda, we're now going to show that this sort of Yoneda isomorphism psi is also natural in functors. And again, this is surprisingly straightforward. So we have these different objects, and somehow these things and these things are functorial in the actual functors that we're plugging in them. And then we're considering this psi here to be a sort of natural transformation between these, from these kind of functors to these kind of functors. Well, this is the inverse of psi, which is this natural transformation. So what we're doing this time is similar to what we just did, but now we're going to hold the object E fixed, and we're going to vary the functor. And we want to sort of think about what it means for this square to be natural. Okay, so what's that mean then? Well, it basically means that we ought to have an arrow from G to H, okay, because we're thinking, well, in our source category, which now we're really thinking of as the category of functors from C to set, we're thinking, well, we have an arrow. We have an arrow from a functor G to a functor H. So it's going to be a natural transformation. We're going to have a natural transformation delta from G to H. Here's a picture of what something like that might look like in the category of graphs, but we're talking in generalities now, okay? And it's actually quite easy to see in this case that the thing really is natural when we vary these functors, okay? So what happens then? Well, we need to construct this naturality square. So here's what happens when we operate this kind of nat hom functor thing on our functor, and we get this set of natural transformations from hom e dash to g. And then somehow we need to lift this arrow here from functor G to functor H under this funny kind of functor here. And that sounds complicated, but it's actually not that bad, because what we have here are sets, and so we know that this is going to be some kind of a function which sends a natural transformation alpha from hom e dash to G, and it sends that to a natural transformation from hom e dash to H. Okay, so we really have this kind of picture. We're starting with a natural transformation alpha from hom e dash to G, and we also know there's this natural transformation delta from G to H. So how can we use these to make a natural transformation from hom e dash to H? Well, we can simply do alpha, we can simply do delta after alpha. Okay, so if we just send alpha to delta after alpha, then that'll do the job for us. Okay, it turns out that that's the kind of function that this natural transformation delta gets kind of lifted to. It gets lifted to this kind of function which sends a set like this to a set like this by sending an element alpha to delta after alpha. And actually, if you sort of look at this form and then compare it to the contravariant version of Hom Functors, which I'm going to introduce at the end of this video, and think about how this is to do with sets of essentially sets of arrows in this functor category, then this will actually seem very natural to you at that point. Anyhow, that's how this lifting works. And so how about this one? How do we lift this arrow delta, which goes from G to H, to some kind of an arrow which goes from this object here, G of E, to this object here, H of E? Well, how can we use a natural transformation delta to go from G of E to H of E? Well, that's simple. We just take the eth component of our natural transformation, and that'll be an arrow from G of E to H of E. So that's what this arrow looks like. Okay. So all we have to do now is argue that this is a naturality square to show that this kind of Yoneda isomorphism is natural in the functors. So how does it work then? Well, we'll just load a generic element into this top set. I'm just writing a red alpha here to represent an element of this. And then we're just going to show that doing this function and then this function gives us the same result as doing this function and then this function. So let's go the top way around. We have alpha. We do psi to the minus 1 of it, and we get alpha of E of IDE. That's here. Okay. Now we just do delta E of it. We get delta E after alpha E of IDE. So that's going this way around. Now what about going the other way around the square? Well, alpha, and then when we do this function on it, we get delta after alpha. And then when we do this function on it, we get the same thing. We just get delta of E after alpha of E of IDE. So that's pretty much all there is to it. How can we interpret this in our picture of graphs? Well, here's our natural transformation alpha from Hom E comma dash to G, and then going along here, that gives us this edge E star, and then going down here, that does the eth component of delta, so it just sends A equals E star to A bar in this graph. So the other way of getting at this edge here is to sort of do the natural transformation delta after alpha. So that's just both of these composed together, and then find out where IDE gets sent to under that. So of course that's referring to the same edge. Okay, so now we've seen a demonstration of why the Yoneda lemma is natural. A couple of things I should say. I noticed that I've been going a bit wrong with my notation. I ought to have been using dots because these are vertical. I ought to have been using these closed dots because these are vertical compositions of natural transformations, the easy ones. Okay, so there's a lot to go into here. I mean, I think it's such an interesting exercise actually to just go through the Yoneda lemma, the different things I've discussed today, claims about things being natural transformations, claims about things being isomorphisms, descriptions of how things work, and just to actually go through some of these examples yourself. I think it's a very, very worthwhile exercise because, I mean, number one, it gives you so much exposure to all of these important ideas in category theory or working together. And secondly, I mean, the Yoneda lemma is one of the most fundamental results in category theory. It's one of the most useful ones for computation. I've been discussing it a lot in terms of these functor categories, particularly the category of graphs. But, you know, it is true that the Yoneda lemma is very useful for understanding functor categories of functors into set. But it has lots of other uses as well. Okay, it's used all over the place in many different creative ways. And I mean, I think this is such a peculiar result, actually. It's, I mean, so many mathematical results look like generalizations of things that came earlier. I mean, the Yoneda lemma could be considered to be a sort of generalization of I think it's Cayley's theorem from group theory, but it's such a massive generalization and it's weird. I mean, it's not like most other results, and I think we're really in the early stages of appreciating what this result actually means. So, I mean, if you're so inclined, I really encourage you to go into this and explore some new areas of this result for yourself, because I believe there's still lots of low-hanging fruit to be picked. Okay then, so understanding the category of graphs is one of the lovely applications of the Yoni lemma. By going through what it means, we really see how we can refer to the structure of graphs internally and externally. Now, this category of graphs, which we usually write as set to the power of this category with two parallel arrows, that's just one of these categories of functors into set. Another one, a very lovely one, is this one. This is the category of dynamical systems, and the Yoneda lemma can be applied there as well, and if anything it's even more beautiful in this case. Now, time is getting on, so I don't really have time to slowly explain how the Yoneda lemma works in the category of dynamical systems, but I'm going to go through a brief sketch of it, and I really encourage you to fill out the details because it's just so nice, okay, in my opinion at least, because it's just such a interesting kind of thing, and it's very lovely actually to figure this out for yourself. So let's just recap then. How does this category of dynamical systems work? Well, the objects are functors from this category here to set. Okay, so what's this category here? Well, it's sometimes called the additive monoid of natural numbers, or a free monoid with just one generator. It's actually a pretty simple thing. It's just one object, and of course we have an identity arrow. I'm calling this object star. And there's also one non-identity arrow called S. And in addition to having S, we also have S after S, S after S after S, and so on. All of the different kind of iterates or compositions of S with itself as many times as you want. Okay, so when you think of the identity arrow as doing S 0 times, and this is doing S once and twice and thrice, and we can do S as many times as we want, and we never get any other arrow from doing that. We always get something new by composing a sequence of S's with another S, okay? So in a way, it's sort of like the natural numbers. This is almost like a kind of successor operation. Anyway, what's a functor from this category to the category of sets? Well, it'll send this object star to a set, and it'll send S here to some function, g of s, that goes from this set to itself. And it'll also send S after S to the thing we get by applying this function twice, and this will get sent to what we get if we apply this function 3 times, and so on. And that's why this is called a dynamical system, because S really gets sent to something that we can think of as a kind of update function. So we could visualize this this functor like this with a couple of sets and this function here. Maybe better to give it a kind of internal diagram like this. I mean, we have these elements, and then we just internally draw how this function maps these elements, and we can think of iterating, as in repeatedly applying g of s, as just kind of walking around on these arrows. Okay, so A gets updated to become B, and so forth. Okay, so this is one dynamical system. This is one of these functors. Here's another one. I'm calling this one H, and here's an internal picture of it. What do the arrows look like in this category? Well, they're just natural transformations between these functors. Okay, so basically what an arrow is going to be is a function from this set here to this set here, which has the property that if you do the transformation and then you do the update, you get the same thing as if you do the update over here and then you do the transformation. So an example would be sort of folding this picture here onto this picture here. So if we send A to B bar, B to A bar, and C to B bar. I believe that works. So let's just draw it out over here. So A gets sent to B bar. So this would be the only component of this natural transformation, okay? So what happens? A got sent to B bar. B got sent to A bar. And C got sent to B bar. So hopefully you can check that this is a natural transformation. For example, A gets sent to B under the update and then gets transformed to A bar, and A gets transformed to B bar, which gets sent to A bar under the update, and so forth. So okay then, what does the Yoneda lemma tell us about this category of dynamical systems? Well, basically the way that I think of applying the Yoneda lemma to these categories of functors into sets is basically find the Hom Functors, find what kind of structured sets they represent, and consider the arrows out of them, and that'll tell you about the other things in the category. Okay, so there's going to be a Hom Functor for every object in our category C. Well, that's easy, there's only one object, so there's just one Hom Functor. What kind of dynamical system does that look like? Well, I'll leave it to you as an exercise to convince yourself, but basically it looks like the natural numbers. We're including 0 here, and 1, 2, 3, and so on. And so it's going to be the set of non-negative whole numbers, or at least we can think of it like that. And then the update function is just this successor function, which sends 0 to 1, 1 to 2, 2 to 3, and so on. So it's this very kind of natural kind of dynamical system. And it turns out that this is what our Hom Functor looks like. So what's the Yoneda lemma tell us? Well, it tells us that natural transformations from this sort of dynamical system of counting, this Hom Functor Hom star blank, into another dynamical system G, this set of natural transformations is going to be isomorphic, naturally isomorphic, to the actual set of elements in our dynamical system. Okay, so what's this telling us? It's telling us that arrows in this category of dynamical systems from this sort of counting dynamical system into another one are in correspondence with the states of the system. And how does this work exactly? Well, let's think about a arrow, or a natural transformation if you like this. So we can send 0 to anywhere we want. Let's send it to element A, okay? Now, actually the kind of constraints on this being a natural transformation forces the rest of our natural transformation to have a particular form, because we know that updating in the counting system and then mapping ought to go to the same thing we get if we map and then update. So we know that 1 has to go to B, and 2 has to go to C, and 3 has to go to B, and 4 has to go to C, and so on. Okay, so the whole trajectory gets forced by the way that we decide to map 0. Okay, and we also have this very interesting feature that kind of updating in here and then mapping is essentially emulating doing an update here. But there's more to it than that. You see that there's exactly one of these sort of transformations for every state of our dynamical system. And the whole transformation, the way it works, kind of tells us the future trajectory of our system. So we have this lovely kind of correspondence. And it also allows us to sort of refer to what's going on in a dynamical system from a kind of external standpoint. Okay, so what we can do, we can think about a natural transformation from this Hom Functor to itself. So what about if we send 0 to 1, then we have to send 1 to 2, and 2 has to get sent to 3, and so on. So we can call this natural transformation sigma. And what about if we have another natural transformation from this Hom Functor to G, which is actually the composition of these two, okay? Well, it's going to send 0 to where beta sends 1. So it's going to send 0 to B. And it'll send 1 to C. And it'll send 2 to B. And so on. So if we call that natural transformation gamma, then what we're going to actually have is that gamma of 0 is equal to beta star after sigma of 0, which is equal to beta star of 1, and so on. And so just by specifying that this gamma is the composition of a kind of counting +1 transformation and then beta, we're basically saying that this gamma is the transformation we get which represents this kind of trajectory here wound on by one time step. So we're essentially talking about the updating that's happening in this system and the states and all the rest of it in terms of these arrows from this functor Hom star, which is basically representing the natural numbers. So it's really very, very entertaining, I think, to actually go through and look at this category of dynamical systems and really see how the claims of the Yoneda lemma mean things in this category, because it basically informs you of the fact that you can really talk about what's going on in a dynamical system just by thinking about the arrows into it from this special kind of functor here, this sort of dynamical system of natural numbers, this kind of counting dynamical system here. Okay, so now we know the Yoneda lemma, we can just quickly sort of double our money by exploiting duality, because there's another kind of dual result called the Co-Yoneda Lemma. So everything I've talked about so far, the functors involved have basically been covariant, the kind of normal type of functors. But the other type of functors are these contravariant ones, which essentially kind of reverse the directions of the arrows. And the Co-Yoneda lemma works when we have a contravariant functor G. And what it says is, in this case, the set of natural transformations from Hom dash comma E to G is naturally isomorphic to G of E. So it basically looks the same as the ordinary Yoneda lemma. It's just that we've kind of reversed the positions of our object and the blank. So we're now talking about the kind of other type of Hom Functor here. This Hom Functor, when it operates on an object, it sends it to the set of arrows from that object into E. So Hom Y comma E will be the set of arrows from Y to E. And this is actually, this type of Hom Functor, the kind of other kind of Hom Functor, is actually a contravariant functor, okay? Because if we have an arrow F from an object X to Y, then when we lift that, we'll get this arrow Hom F comma E, which goes from Hom Y comma E to Hom X comma E. How does it work? Well, it's a sort of function which sends arrows from Y to E to arrows from X to E. And hopefully you can see by this picture how it works. If we have an arrow little y from capital Y to E, then when we do this sort of lifted arrow under our Hom Functor on that element little y, we just get y after f, which will indeed be an arrow from X to E. Okay, so now we know about the Yoneda lemma, and after doing all that maths, I feel kind of licensed to be able to talk a little bit about philosophy. Indeed, I may get a little bit carried away, but please bear in mind that these are just my own opinions, and you know, that's just it. But basically, in my opinion, what the Yoneda lemma is saying is it's saying that there's two kind of ways to refer to things. We can refer to them from a kind of internal perspective or from this kind of external perspective. Now, of course, from what I've demonstrated so far, we just see that this is true of the kind of functor categories, these categories of functors into sets. But these are basically describing structured sets, and there are so many of them. They describe, you know, there's different kinds of structured sets to represent so many mathematical objects that we think about. And the fact that this kind of internal / external kind of duality exists for all of those kind of categories of interesting mathematical objects, in my opinion, means that this is a deep result about reality. Now, what does it mean? Well, I think it points to a kind of duality between the kind of internal structure of things and the external structure of things, or Hermeticism. For example, there's one of the main sayings from Hermetic teachings is as above, so below. Well, it kind of indicates that there is this sort of quality in these categories of functors. For example, the way that a graph is internally is a sort of reflection of the way that the other graphs around it are externally and how they are related to it. It also reminds me, while we're talking about kind of ancient ideas, it reminds me of a sort of, I think it's a Buddhist kind of idea of Indra's pearls or Indra's necklace. Basically, this kind of metaphor for the universe, that it's sort of like a load of mirrored balls, and within each mirrored ball is a reflection of all the others. And so reality is built out of a kind of load of things which are reflecting one another, making a kind of fractal aspect and so on. And it indeed seems like maybe mathematical structures are arranged in this way. What's it mean for real life? Well, maybe one could almost say that it's a sort of justification for being good, in a sense. If reality is structured so that the kind of internal goings on, let's say, for example, in our bodies, are reflections of the way that we interact with things in the world, then that's a good reason to be good, right? Making a good environment around yourself will make your internal kind of states good. What's it mean sort of in a more down-to-earth way? Well, I see parallels with particle physics. I mean, the idea of particle physics, as I understand it, is that we're looking for these kind of elementary particles which the other stuff is made out of. What's the analogy of that in our functor categories? Well, it'd be kind of like finding these Hom Functors, these things like the single vertex or the single edge, which the other graphs were made out of. And what does the Yoneda lemma tell us? It tells us that the kind of internal structure of things is just a reflection of how they kind of interact with the particles, and also that the kind of particle interactions and the way that those particle interactions relate to the flux of stuff coming into an object kind of defines the internal structure of that object. So if something like the Yoneda lemma is true of our universe, we should probably expect that the way that elementary particles interact with each other is related to the way that elementary particles are bound to each other inside objects. Now, all of this is just my own speculation, but it really makes me think, for example, in other subjects, like, say, ecology or psychology, might other kinds of analogous things be true? Might there be kind of elementary things which are kind of like the basic entities in those subjects which interact with each other and the other objects and kind of like project the structure inside, and kind of like projects the structure of the other objects that are going on. Might it also, and I kind of get a bit carried away, I wonder if I wonder about things like this sort of view that we have as humans generally, that the things around us are made out of bits, they're made out of elements in sets and so on. And it seems to be the kind of unsaid kind of idea in mathematics that is the basic way that mathematical objects are. Most basically, they are a load of stuff which is interrelated somehow. But with the Yoneda lemma, we kind of see that actually when we have something like that, like a structured set, its internal structure is just a sort of reflection of the relations that mathematical object has with other things. So might it be that this case of things being made out of stuff kind of internally is actually not the rule but the exception? Might it be that the kinds of objects we generally think about are structured sets, and that's why we always view them as being made out of stuff? Might it be that the more general kinds of mathematical objects, like, say, objects in a category which is not a functor category, are actually primarily defined in terms of their relations with other things? Might it be that our idea of things being made out of stuff, could it even be illusionary? Could it even be that, you know, at the basic level, when we're talking about quantum mechanics and so on, what we really just have is a load of relations between things, and somehow our minds imagine that means that things are made out of concrete internal structures? All just complete conjecture, but I find this Yoneda lemma very kind of, it really makes one think about stuff like this.